Hey everyone, I'm Ash. I actually exist outside the confines of this video, but I'm going to stick around in order to talk to you about delivery guarantees in stream processing, because I think the terms that we use are trash. I think that they result in us building and adopting tools that aren't as reliable as we think they are, and therefore they are literally destroying society. I'm not going to focus on calling out any particular services or tools in this video because A, I might have misunderstood them, B, things change, and also I don't think it's particularly productive because these are issues that I see not only in production services that we've widely adopted, but also services that get built in-house by data engineering teams frequently. So what I want to do is I just want to go over all the common bugs that I see and misconceptions and just give you an idea of what are things to look out for when you're picking services and tools, and also how to avoid introducing these issues in the things that you build yourself. To get started, I'm just going to do a very quick overview of what stream processing and delivery guarantees are for the kids that just graduated. So when we're talking about stream processing, we're talking about a system where we have some service that is writing a continuous feed of discrete message, event, log, whatever you want to call it, payloads to something else. And that's happening over some sort of network connection. So it is prone to errors and faults under various circumstances. And the important thing for us is to understand, well, when we're running this system, what happens during those errors? What can we expect? And we use delivery guarantees to describe that. I'm going to cover the main two right now, which is what covers most stream processing services. I'll tackle some others towards the end of the video, but these are the ones that are the main culprits of issues. The first one is describing systems as at most once. So an at most once delivery system is where we're sending messages to a destination, but we don't really care if the messages end up at that destination. And the idea here is that in the event of some sort of fault on the network or downstream components just coming offline, we just drop that data. And you can kind of consider it like, basically blindfolding the system that's sending these messages out, because all it's doing is a sort of fire and forget. The term at most once indicates that we will never introduce duplicates into the system, and that is at face value what you would expect from an at most once system. So if you don't want duplicates to be introduced in your stream, this is maybe an option for you. In practice, they almost always have circumstances by which they might duplicate data. So you can't really rely on that in practice. Most at most once systems are used just because we don't care about message drops, so we would rather have services run a little bit faster. And in the event of errors, we just want to keep the pipelines running and clear rather than backing up traffic and having back pressure and requiring manual intervention. So this is very common in logging infrastructure, for example, where we might not really care if some of the data gets dropped. I'm not going to dwell too much on at most once because even though there are misconceptions with at most once systems, they're fairly low stakes because, like I said, most of these systems are just kind of hackily put together, and the people running them don't really care what the quality of the data feed is necessarily. The next one is at least once. Now, this is the one I'm really going to focus on in this video because this is the main source of misconceptions and misdeeds and villainy. And the concept here is that we're describing a feed where in the event of errors and faults, we would actually rather introduce duplicates and send messages again than risk dropping data. So the implication here is that we would never drop a message. We will always make sure messages get delivered at least one time. The way that that's almost exclusively implemented is with some system of acknowledgement, where the data will get sent to a destination and then it's on the destination, the receiver of the data, to send some sort of message back in the form of an acknowledgement of the receipt of that message. And if that doesn't come back ever, or within a period of time that we've agreed upon, then the service that's sending the data is expected to send it again. So it has to persist that data somewhere while this is all happening. And it's the responsibility of the service that's sending these messages out to make sure that a duplicate is sent out rather than just assuming the data has ended up somewhere. So the first major misconception with the term at least once that I want to tackle here is the fact that it sounds very absolute. When you're describing a system as at least once, it sounds like you're saying that all messages will be delivered at least once and therefore never dropped under any circumstances. It's kind of comparable to a claim like lossless data compression. The difference there is lossless data compression is something you can prove, and it's absolute. If a compression algorithm is lossless, you can compare it to any other compression algorithm that's also lossless. They will all be equally lossless, which is absolutely lossless. That's not the case with at least once delivery guarantees. There is no system on the planet that can guarantee it won't drop data under any circumstances, because we're no longer in the realm of mathematics here. We are dealing with real world events and handling those edge cases with networked distributed components. So you can take any number of at least once systems and compare them in terms of how good they are at being at least once. They will all be wildly different. To illustrate that, I've got a diagram here. This is a mountain where I've just written on it from the bottom to the top a bunch of different events, real world events that could happen to a service that describes itself as at least once, that could maybe trigger data loss. And the idea is that right at the bottom we've got the easiest ones to handle, and then right at the top we've got the more difficult ones or impossible ones. You could take an at least once system and you could basically plot it somewhere on this mountain. It gets to a certain height before it's no longer able to guarantee delivery. I'm just going to run through these quickly because it's not particularly interesting. But basically, right at the bottom, we've got the service is just restarted. That's the bare minimum, right? If you've got a system that describes itself as at least once, but it might drop data quietly if you've restarted it. In my mind, it shouldn't be able to describe itself as at least once, but that's not necessarily the case. And I'm sorry to say, very sadly, there are services that are widely adopted, or client libraries, frameworks, that kind of thing, where they will result in data loss if you've restarted it at the wrong time. I will go into details in this video as to how that comes about. I'm not just going to leave you hanging there. The next one is the service crashes. So this is only slightly more difficult to deal with than the service restarting, but obviously you're in a situation now where you can't predict what state the service is going to be in. In my mind, these are the bare minimum requirements. If a service, when it's plotted as to what it can deal with, isn't able to overcome these two hurdles, then I really don't think it should be able to describe itself as at least once. But unfortunately, that's not currently the case in the data engineering world. The next one is that the machine isn't gracefully stopped, so the plug's pulled or it crashes. That's basically the same circumstances as service crashing, but obviously it's now out of your control. So in theory, you could write a piece of software that isn't crash resilient, but it just doesn't crash. Dubious claim, definitely, but maybe you could envision that being the case, but you can't anticipate the machine being ungracefully stopped, so you might as well just design your systems to be resilient against crashes anyway. The next one is the disk becomes corrupted, so the disk that might be used by a service for persisting some sort of state, if that gets lost, if it's deleted, or if it just becomes corrupt, then if the service that's using that for ensuring delivery guarantees can no longer do so, if that data is gone forever now, then it wouldn't make it this high up on the mountain. Everything after this is basically just an evolution of that. So the next one is a data center blows up. So if you've got a service that relies on persisting some sort of state, and it can survive corruption on one disk because it's got some sort of redundancy built in. But if all that redundancy exists within a single data center, then obviously if the data center blows up, then you can't guarantee delivery of that data. This is more of an operational thing, but obviously if the service itself it doesn't allow you to have some sort of redundancy, then you can't reach this point, even if you wanted to deploy redundancy. The next one is the country outlaws tech and EMPs itself. So this hasn't happened yet, I don't think, but if a country just decides, oh, we're done with tech, it's too much hassle, and they decide to send out an electromagnetic pulse that just kills all electronics, then obviously that's a bit more extreme than a data center blowing up. And obviously if you wanted to overcome that and retain your data, then it would have to be replicated with redundancy outside of the country. The next one is the moon crashes into the earth. So at this point, I don't think there's any system that exists that describes itself as at least once that wouldn't lose data in this situation, unfortunately. It doesn't matter how good your Kafka deployment is, how many brokers you've got, how much redundancy you've got, unless you've managed to find some performant way of getting redundancy outside of the planet. maybe in some sort of satellite. It would need to be sufficiently far away to not be affected by the blast radius of the collision. But unless you manage that, you're going to lose some data, I'm afraid. And then finally, Lord Veth 22 returns. So when this happens, obviously all bets are off. We might as well just accept that data loss is on the table. Unless you've managed to somehow get your data out of the solar system, it will be embraced, as with our souls, by Lord Veth's tractor beam, as he brings us all into our final destination. So imagine you're just plotting all the services and tools that we have in the data engineering industry, tools that are adopted, and also tools that are built in-house. If we were to plot them on this mountain by the lowest requirement that they fail at, I think unfortunately a lot of them, if we're being real, will be somewhere near the bottom. And that might not necessarily be something that we're aware of, or the author of these services is aware of. But unfortunately, there are many edge cases and misconceptions that kind of enable this, which I'm going to go into now. So this leads us now into the second major misconception with delivery guarantee terms, which is they focus entirely on delivery. It's delivery guarantees, at least once delivery, at most once delivery. We're always talking about these guarantees in the context exclusively around delivery of the message. Now, it's true that any guarantees around stream processing has to start with delivery, but that's the least interesting part of stream processing. The delivery is just the first bit. All the interesting stuff will always come after it because we've delivered the message for a reason, and now we need to enact those reasons, which is the side effects. But the terms themselves, they only deal in delivery. We're only describing a system in terms of its delivery. I've got a little comic here to illustrate the problem. It's only 2 panels, so it shouldn't take you too long to read. But the first panel here is message delivery happening. So we've got services blue and red. They both describe themselves as at least once delivery. And the message gets delivered, and then panel number 2 is the side effect. So the side effect is whatever we need to have happen to that message. In this case, it's the message gets read and then there's an emotional response. And that's the bit that we actually care about. We only care about the side effects. We don't care about the delivery in the context of this comic. The side effect is the thing that we actually need to have happen. And therefore, that's the thing that we want to guarantee effectively with our delivery guarantees. However, if we were to take delivery guarantees at face value, then there's nothing to say that service in red can't acknowledge the message in panel 1 because the message has been delivered. So if it acknowledges it at that point, we still have at least once delivery, everything's fine, right? But if that's the case, then if we were to crash the comic at the end of panel 1, then the next time that we start the comic, neither of the panels execute because panel 1 starts and the message has already been delivered and service in blue has received acknowledgement for it, so it's not going to send it again. So panel number 1 doesn't happen the next time, and therefore panel 2 has never happened. It didn't happen the first time we ran, and it won't happen the second time we run. So we've effectively lost the data in the context of its side effects, and that's the thing that's important to us. We don't care about the delivery. What we should be doing is we should be implementing some sort of at least once side effects by only acknowledging the message at the end of panel 2. Once all the side effects have been finished and resolved, and we've confirmed them, and if we do that, then it doesn't matter where the crash happens within this comic. The next time we start it up, the side effect will always have happened at least once, maybe multiple times, but at least once, right? And that's really what any service that's describing itself as at least once, in my books, is effectively promising to us when we're delivering it. That's what we're thinking of. We're thinking everything that we expect this piece of software to do to a message is going to happen at least once. But the delivery guarantee itself is only in the context of delivery, and therefore these services often describe themselves at least once, even though they don't do that. They don't do the side effects within the context of an acknowledgement. They only guarantee delivery, which I think is naughty, frankly. I see this most of the time when we're using off-the-shelf solutions like Kafka, which is perfectly fine in this regard. It's super resilient and obviously deals with acknowledgements properly. But the in-house solutions that are consuming from Kafka are doing things like auto commits, and therefore you can't guarantee that a message has made its way all through your side effects before the offset was essentially stored within the Kafka brokers. I also, unfortunately, see the same problem with off-the-shelf stream processing solutions. So they will acknowledge receipt as soon as it's read data, and then anything that happens after that is basically all bets are off, depending on the state of the software and these edge cases. Those pieces of software will often describe themselves as at least once, but we just don't have end-to-end guarantees yet, or it's something that you can maybe add some bells and whistles on top, maybe a pro solution or something like that, where you do get those, but most people don't care about that, so don't worry about it. To that, I would say, imagine I have a house and I've got a super secure front door. It's made of thick steel, it's got a camera on it, it's got locks and all that stuff, but all the windows have been smashed through. If I told you that this house is secure, we just don't have end-to-end security yet, I don't think you would accept that. I think you would tell me to jog on and you wouldn't spend the night there, right? I think we should approach at least once delivery guarantees in stream processing solutions the same way. If your guarantees stop at delivery and don't go any further, if it doesn't cover the entire breadth of the scope of this service and why I'm using it, then you might as well not have it in the first place. You could have just gone for at most once delivery, and that's going to look exactly once in normal operation anyway. So why would I even bother having at least once delivery and going through all the trouble of setting up all this complexity if you're not even fulfilling end-to-end acknowledgements? This kind of ties into the next thing I'll say is that we tend to have a focus in the stream processing world when we're thinking of a pipeline of components as the strongest link is the important part. So we can make our pipeline more resilient by having Kafka, replication, redundancy, all these brokers, putting a huge amount of investment into the messaging infrastructure that we're using to chain all these services together. But in actual fact, the services that we're using to utilize these queue systems have weak delivery guarantees. They don't have end-to-end acknowledgements either at all, or they're using something like a disk buffer to they'll write data to a temporary buffer with disk persistence, acknowledge the message then, or commit the offsets, that kind of thing, and then they'll process the data while it's on disk, and then when it's finished they'll delete it on disk. That's fine, but there's no point having replicated data with redundancy if you've got this lossy aspect of your pipeline that could be losing data you won't even know. Like, it could be losing data continuously all the time. A message a month just gets dropped and you won't have any knowledge of that. Maybe you've got a retention policy in your Kafka brokers of a month, but for a year you've been running it, and some lossy aspect of your pipeline, some weak link in the chain has been letting you down, and you had no idea. What's the point in investing all this time and energy into the strongest links in the chain if you're not going to address the weakest links? We should have this image in our head of the delivery guarantee of a pipeline is only as strong as the weakest aspect of it, because that's the reality. That's where data is going to get lost. If it's going to get lost anywhere, it's going to get lost in the weakest links during these edge cases. Now, one common way that this manifests in a more abstract way is consumers of Kafka with auto-commit, where mentally they think that they're fine because they commit offsets every 5 seconds or something, and the cadence of those commits is much, much bigger than the time taken to process a typical message. So say you process a message in like a microsecond, and therefore that's well within the time constraints of these offsets being committed. So you can mark an offset ready to commit as soon as you've consumed the message. It gets processed, assuming within a nanosecond, and then committed. There's two problems with that immediately. The first one is, well, you might read the message, mark the offset ready to commit, and then it just so happens that the 5-second timer triggers a nanosecond after that. Obviously, that's very difficult to force to happen, so it's difficult to test for. But in theory, it could happen. The more likely scenario, though, is that a problem message is going to block. It won't get routed anywhere. Either it's causing some issues in the service itself and it's grinding to a halt, or the output destination, the side effects you're trying to execute, are blocking. They're pushing back and saying we can't process this data, or they're just unavailable. And then that 5-second commit, auto commit happens, and at some point a human has to intervene. Oh, there's some issues in the pipeline or whatever. That might include shutting down the service and starting it back up again. Or maybe it just crashed because there was some edge case got triggered and something weird happened. The next time it comes back up, it's not going to consume that message because you marked it ready to commit, so it got committed. And the consumer will naturally start after that position. If you aren't aware, as the operator of this service, that this piece of software is just naturally going to skip data under certain circumstances, then you might not know to reset the offset. Why would you? And you might not trigger a backlog, a backfill, or any of the other defensive maneuvers for recovering data. And then finally, another manifestation of this issue is when you've got multiple side effects. So imagine we extend our comic and we add a third panel with more side effects that need to happen, and that's sending messages and delivering it to multiple destinations. So you've got multiple network side effects that could all be happening in parallel. So you could be sending to two different queue systems, or it could be hitting some database and then sending data elsewhere. This gets complicated because one output might be available and responding and the other one isn't. What you should be doing is applying back pressure at that point because you can't deliver data. And if you're meant to be delivering data to both destinations, if one of them, it doesn't really matter, then obviously you can just skip. You can effectively treat that as an at most once delivery output. But if both outputs matter, then obviously you need to defer the acknowledgement until both of them have received the side effect. And I see it's quite common for people who are building this stuff, because it's quite complicated to keep track of all this stuff and have like a proper fan out broker and keep track of everything that's going on. It's much easier to just acknowledge messages when it's been delivered somewhere. You've had some thumbs up from an output destination, but obviously that still puts you in a situation where you don't have strong delivery guarantees. You've got a weak link in your chain somewhere. Now, next up is a juicy one. This is a nice bug. I see this is a specific one to Kafka, or I guess any ordered log processing system. But basically, we're in a situation where we're reading from a queue and we want to use vertical scaling across CPU threads. So a very common scenario with systems like NATS and AMQP, the way that these queue systems work is that you can just arbitrarily read messages, discrete payloads, and you can acknowledge them individually. So when you acknowledge a NATS message, you're acknowledging that specific message and none others. There's no consequences to any of the messages in the system. That makes it very easy to scale vertically. So you imagine you've got loads of CPU processing threads, and you want to utilize those. You can just distribute those messages across those threads, and they can all be acknowledged individually. There is often, with a lot of these systems, ways of having ordered guarantees, because obviously with a system like this, you can't guarantee the ordering of the messages. And there's often some way of adding an abstraction layer on top that takes ordering into account and gives you some safety there. But by default, they're not ordered, and you don't have to worry about that on the client side. Kafka is the opposite. In Kafka land, we have a topic spread across partitions. And that's all configurable. We can have as many partitions as we want. And a partition is essentially a sequence of messages that are consumed in a specific order. And as you're consuming them, you're not acknowledging necessarily an individual message as having been consumed. What you're doing is you are saving your position on that partition. And the idea is that messages can be fanned out. We can get some sort of horizontal and vertical scaling by fanning messages out across partitions, but each partition contains all the messages that are needed for a particular ordering of. So you imagine like customer orders would be routed to a single partition based on some sort of key that joins them all together. This makes the vertical scaling options more complicated because so here we've got a scenario where we've got 3 partitions, but we might want to scale those across 8 processing threads, something arbitrary like that. The problem is when we can't control how many partitions there are going to be. Either that's managed by a different team, or we just can't change it. We can't increase it or whatever. What are we to do? I need to get my 8 processing threads. What I see happening very often is systems will still just willy-nilly fan those messages out of a partition to separate processing threads, and they all get dealt with asynchronously. The issue comes in when you think about when do they mark offsets, because in the place where we can just deal with each message individually, then each asynchronous thread, when it's finished with its message, it can just acknowledge it and it doesn't interact, it doesn't affect anybody else. In this scenario, that's not the case, because when we mark an offset ready to commit, we're also saying that all messages prior are also committed, because we're saving a specific position. So imagine, let's just zoom in on one of these partitions in particular. Imagine we've spread these 4 messages that are a sequence across 3 processing threads. So one of them claims 2 and the other 2 threads claim 1 message each. The one at the end here, the one marked green, has done its job quite quickly. So it's processed a message. The message has gone through all the happy paths of the service, and we've executed all the side effects. We're now ready to commit that offset. So we do so, right? That's a problem if the thread processing the message that's prior is blocked. If it's either a big payload and it takes much longer to process, or maybe it's blocked somewhere, it's a bad payload and the destinations we're trying to send it to are rejecting it. So we're in some sort of like retry loop now. Either way, if it's not finished before the thread marked green is finished, and the thread marked green marks the offset ready to committed, and then the service comes offline and back again, then we've dropped that data. That message is gone forever. And this is a scenario that can manifest just through restarts, and you wouldn't know. There's not going to be any indicator that a problem has occurred. The service is just going to quietly come back up, and it's going to quite happily just continue where it thinks it left off, and that red message gets skipped. This is particularly dangerous because you don't even need service restarts necessarily. A partition rebalancing that could be triggered by any number of reasons, and is just something that's going to be continuously happening in the background potentially, that would also drop that message potentially. So yeah, this is a super nasty one. This I see frequently in in-house built solutions that are kind of using Kafka client libraries, but they're doing their own thing in terms of how they distribute processing. Unfortunately, though, I also see this in libraries that abstract over the top of Kafka client libraries for various languages. They will act essentially on your behalf of guaranteeing delivery. They describe themselves as an at least once processing framework for scaling, and they'll be doing this, which to me is terrifying, because anybody using that framework, which is describing itself as production ready, it's describing itself as at least once, could be losing data every time their partitions rebalance, that's mind-blowing to me that this is okay. You might be thinking, well, what's the proper way of dealing with this? Because that looks that looks naff, right? There's quite a few ways. So the first one is you read messages in batches, and then you just fan that batch out, and a process keeps track of when the batch is finished as a whole, and then it commits that offset then. That's one way of doing it. It's a bit clunky. It means that your processing isn't like a nice, smooth, continuous thing. So some people don't like that. I personally don't like it either. The other way of dealing with it is so what I've done in the past is I've had like a tracker that is owned by you, the service. It's in process, and effectively that's just like a layer on top of marking offsets ready to commit, where it keeps track of a continuous list of offsets, and when they get acknowledged, it essentially removes them from the chain, and it makes sure that the absolute lowest offset that hasn't been acknowledged yet is still kept track of, and we will only mark an offset ready to be committed if all prior offsets have been marked. That's obviously a little bit more complicated because you have to deal with things like applying back pressure. If imagine you can't process a message, well then you have to stop at some point, otherwise that list will just keep growing. And when potentially if you restarted the service after like an hour of doing that, then you would run a backfill essentially of all that data. So what I tend to do is I have like a configurable number of messages we're willing to have processing in flight after the lowest offset that we're able to commit. So if one message is just stuck in some state, then we're not just going to keep continuing down the partition for too long. But yeah, I mean, there's other ways of dealing with it. I mean, to be honest, a lot of the time you just don't need it. You don't need scaling one thread per CPU core processing. A lot of the processing you're actually doing on those messages, you could scale that out instead, or it's not one to one thing anyway. I think a lot of people get too obsessed with the idea of having clean number of processing threads, and it's not that big a deal, everyone. It's better to just have a resilient system and know what it's doing than squeeze every drop of performance out. For most people, some people don't care, and that's fine. So that's all the issues that I wanted to cover in this video. I'm sure there's more out there, frankly. Maybe you can do a video and send it my way if there's some that I didn't know of. Hopefully that's been useful though, and not too stressful. I will say at this point, so I've kind of thrown it out there a few times in this video already, but I think for most people, most teams, a lot of this stuff probably doesn't really matter that much, and I think that's partly why a lot of these dubious claims do go unchecked. I think there's a lot of most applications of stream processing. It's not that big a deal if messages occasionally go missing. Go on, admit it. However, I would say that obviously for the teams that would actually suffer, for the people whose jobs would be in crisis mode, just the drop of a single message, I think we kind of owe it to those people to be more realistic about how we talk about these systems and how we advertise them. But yeah, maybe I'm wrong. Maybe I'm overdoing it a bit here. I did mention at the beginning of the video that I would talk about other delivery guarantees. So one in particular is called exactly once. Now, I think exactly once delivery probably deserves a video on its own, and I might not, because I don't want to think about exactly once, to be quite frank. All I will say on that is that all the bugs and misconceptions and misinterpretations that I've outlined regarding at least once, there is only more when you're talking about exactly once. You can kind of think of at least once and at most once as taking a wobbly system that could wobble in the direction of messages being dropped, or wobble in the direction of messages being duplicated. And the idea is that you're just pushing it in one direction. It's still a wobbly service, that you can't prevent wobbles entirely, but the idea is that you're just pushing it into one direction so that we can at least anticipate where the wobbly service is gonna fall. Exactly once is attempting perfect equilibrium and keeping that service in line at all times. And I just don't think that's realistic. I think that the whole idea of exactly once delivery, even if we're just focusing on delivery, right? We don't even care about the side effects at this point. We're just talking about delivery. I just don't trust them. I just don't trust any of these solutions. The only ones that make sense are the ones that talk about idempotency. And that's the key word. Anything that's talking about idempotency as a concept, those are the ones that are worth talking about and reading about. Just at least exactly once delivery as a concept isn't useful, because it's not real. It's not a real end. It's not a real concept. It can't exist in the world. So the only concept that does exist is the idea of idempotency, which is a side effect executed multiple times will not have any effect after the first. So you can run it. So imagine like an upsert query or something like that. Like basically you're not breaking things by running a message more than once. And that makes total sense, but then I wouldn't call that exactly once delivery. It's got nothing to do with delivery. Obviously there's Kafka transactions, which I think makes total sense. If you've managed to wrap every entity that's consuming that data in the concept of transactions, then yes, you could have a pipeline there that you could describe as being exactly once. But I don't think describing it in any way as exactly once is useful, because, like I said, it's the delivery is only the first bit. It's not interesting as the person implementing these side effects. I would much rather focus my effort on making sure all my side effects in a stream processing solution are idempotent, and then we've anticipated duplicates, and we're okay with that. We've worked around it, and essentially push that logic out into the edges. Than think about exactly once delivery and these odd promises being made by various services, because I just think that's a better use of your time. You'll have much simpler logic in your pipelines, and it'll be much easier to maintain. And I mean, heaven forbid. So if an at least one system drops data, that's at least something that's reasonably manageable from an operations side to recover from. So you can go and seek that data out and replay it, and that's a feasible thing that people know how to do that generally, because you've made sure that you've got a retention policy of a certain window of time. And there's obviously caveats to that, but it's doable. A system where you have side effects that aren't idempotent, so running them multiple times is a big deal. And you're using at least one exactly once delivery guarantees to prevent executing those side effects multiple times. If that promise isn't upheld, either because the queue system that you're using is snake oil and it's not actually exactly once under all circumstances, and you just happen to hit one of those circumstances, or you've just misunderstood what you're doing and there was never a guarantee of exactly once side effects, and you've gone ahead and you've basically built an at least once side effect system that's reading an exactly once queue system, but for whatever reason you have executed your side effects multiple times, that's much more difficult from an operational side to deal with, because it's not just a case of going seeking something out and pushing it back through the pipeline again. Now you're having to untangle whatever mess it's created, and that entanglement there's no end to how complicated that could be. So yeah, I would just stay away from anything that describes itself as exactly once. Either just treat it like an at least once stream, or just don't use it. That's it. That's the video. Thanks for watching. Like and subscribe, and don't forget to go out and enjoy some nature when you can.